Euler field. Or in this exercise, we'll try to provide a geometrical interpretation of the behavior, sometimes strange, of a solid body in rotation. Everything is based on the Euler equation given here, where the vector omega r is a three-dimensional vector which corresponds to the rotation vector of a body expressed in the body frame. So I will try to explain this now. And also, in this exercise, for simplicity, we'll assume that the inertia matrix is diagonal like this, with eigenvalues 1, 2, and 3. And for the first question, we'll have to show that the kinetic energy, given here, is constant. I will consider a solid body, and the solid body is like this. And this solid body is rotating in the space. So here it is the world space. And inside this body, I take a point, a reference point in this body. And this body is, it has its own frame, like this. So it may be anywhere like this inside the body. And the body is rotating, so anywhere like this, around a vector of rotation that I will call omega, like this. So if it is rotating, we can see this vector of rotation omega, given here. We'll express it not in the world frame like this, but in the body frame. So I will call it, for instance, R1. And if I express this like this, it will satisfy a differential equation, which is known as the Euler equation, which is given by this, by R like because it is a body, and in our lesson it is due to the robot, it is a robot itself. So it is given by the inertia matrix inverted like this, multiplied by omega r, vector product E omega r, so again the inertia matrix, like this. And the body, which is here, has some inertia matrix, which in the exercise is assumed to be diagonal, like this. So omega is 1, 2, and 3, and zeros everywhere. So it means that in the body frame, the R is not like this. It corresponds to some eigenvector of the inertia matrix, so it is more like this, like this, and like this. So it is a principal axis of the body. So in this situation, if I choose well the vector of the basis, then the inertia matrix becomes diagonal. So it is what I will assume here. What is important is to remember that omega r is expressed in the body frame and not in the world frame. So for the first question, I have to show that the kinetic energy, like this, which is given like this, so it is given by this relation, I have to show that it is constant. So this result is quite classical, and how I can do this? So I will compute the derivative. The derivative is equal to the derivative of this one, and it will be half. So the derivative of omega r, like this. And here it is a quadratic form with respect to omega r, so I apply the formula of the derivative of the quadratic form, and it is given by this. It is linear with respect to omega r. Now in this situation, I have some simplification, and I obtain I will apply the Euler formula, which gives me that it's given by minus I like this, as I already said, E omega r like this. So I conclude that this is equal to minus so this simplification, omega transpose I given here, multiplied by I minus 1 given here, multiplied by omega r vector product with E omega r. So this is given here. Okay. So after the simplification, this can be simplified by this, and I will obtain that it is equal to minus omega r transpose multiplied by omega r vector product omega r. Now, this vector is orthogonal to omega r. And since here I compute the scalar product between this vector and one vector which is orthogonal, both are orthogonal, then I obtain that it is equal to 0. Question number 2. I have to draw in 3 dimensions ellipsoid corresponding to the set of all rotation vector, omega r, such that the kinetic energy is equal to 10 joules. Then I will have to draw the vector field corresponding to the state equation given on omega r, which is the Euler equation. So for this, I will use a library. So this library, this one, which is available here. So it will generate a OBJ file, and then I will use the internet file 3D viewer for the visualization. So I will generate this file. So I open it. W means I want to write on it. And this file, I call it capital F. Just to show how it works, I will draw a sphere like this. And this is a transformation matrix. So I will try to explain now. This is the color, and here it is a coefficient for transparency. So if it is 0, it means totally transparent, and it is 1, it means not transparent at all. And this is just to draw the axes. So how it works? I have a sphere like this, the unit sphere, given here, with a radius equal to 1. And if I want to draw an ellipsoid, I will give a matrix A and send another coefficient C, just to form the AX plus C. So it is a linear affine transformation, where here I have x1, x2, x3. And here, in this space, the sphere will become an ellipse. So it will become like this, where the center here, 0, becomes here at C, and this one will give another shape to the ellipsoid. So it can be, for instance, a diagonal or a rotation and a diagonal matrix. So I can have the ellipsoid I want. So most of the time it is the product of a rotation matrix and a diagonal matrix. Okay. So if I go here, I run this program, I generate a OBJ file named Euler field, then I go on 3dviewer.net, I open it, this one, and I can see here the sphere. with the axes red, green, blue for omega 1, omega 2, omega 3. Now able to draw the sphere given here. And now I have to find the matrix A and the vector C to be able to have the right ellipsoid. So what I want in my problem, I want to have the kinetic energy, okay, that should be equal to E0, which is equal to 10 joules. Okay, for this, I know an expression for the kinetic energy, and it is given by this. Omega r transpose multiplied by I omega r, and this should be equal to E0. But now, this matrix, this one, is diagonal, but it is also, since it is an inertia matrix, it is positive semi-definite, so there is a square root. So I can write like this multiplied by this. Okay, which is symmetric also. And now recall that if I call this one omega r, if I call this v, for instance, then all this expression corresponds to v transpose multiplied by v, which is equal to the norm of v square. As a consequence, this expression is equivalent to the norm of v, so corresponds to this omega r square, to this is equal, so the 2 here, I put it here, so it will be equal to 2 E0. Okay. So I prefer to write in this form. I will put everything with a norm, so it corresponds to this norm of this vector divided by square root of 2 E0, so I put the norm should be equal to 1. So this vector, I will call it U, and it will be inside this space. So U like unit. So it is a unit vector, because its norm is equal to 1. So this is equivalent to say that there exists a U belongs to the unit sphere, I call it like this, such that omega r is equal to so I isolate in this expression, since U is equal to this, I conclude that omega r can be expressed with respect to U like this, 2 E0 multiply by the inverse of this matrix multiplied by U. So this is equivalent. So it means that I have now the matrix I want. So here, this matrix, for instance, I will call it M. So it means that I have, if I take a vector like this, U, if I apply here, not this, but M times U, and this one is equal to 0, then I will obtain the matrix I want. So I will be able to draw it. So I have to remember this. I will program it. I switch to Python. I have the matrix I want. I call it M. M is now given here, and this vector is equal to 0. I run it. I generate my file. I open it. And I have here my ellipsoid. Okay. With omega 1, omega 2, and omega 3. Now, on this ellipsoid, I want to draw the vector field. So for this, I propose the following program. So I start here. So in my program, I have here my Euler formula, which tells me that omega dot r is equal minus this one multiplied by omega vector e omega r. Because here this matrix corresponds to the adjoint of omega r. Then here I have my inertia matrix, and here the energy I want. The matrix M, and I was able to draw the sphere. Now, to draw the vector field, I will go here in the space U1, U2, U3, and I have my unit sphere, which is given here. So I will scan it. I will scan it with respect to the longitude and the latitude and the longitude. So it is two coefficients which correspond to two different angles I use for spheric coordinates. So the latitude is between my p minus pi divided by 2 and plus pi divided by 2. And it corresponds to this angle. Okay. This is the latitude. And the other one for the scanning will be the longitude, this coefficient like this, and goes from 0 up to plus 2p. Right. And here is a step. So the step, I have chosen here a different step just to have a uniform distribution, because the disk becomes smaller and smaller when I go towards the poles. This is why I have to choose a coefficient to take into account the cosine of the latitude. Then I recall that I have my matrix M, which allow me to go inside the omega 1, omega 2, omega 3 space, and I will go here in the ellipsoid I want. So the ellipsoid I represent like this, which is the image of the unit sphere. And once I am here, so for each point of the sphere, I will go here in the ellipse. And then I will generate the corresponding omega dot r, which is given by this function, the Euler formula. This is why here I use this vector, and to avoid long arrows like this, I will normalize to something which is almost equal to 1. So almost, because here I have this function which allow me, when the vectors are small, like this, not to increase their size. So I want to see when they are small, because it will be important for the interpretation near the equilibrium points. I switch to Python, and I get this program. I will run it. Okay, now I will draw it. It takes time, and I have here the vector field. With here omega 1, omega 2, so I can see here some instability near omega 2, and here I can see that the trajectory will rotate at the neighborhood of omega 1 and omega 3. So I have an instability at the neighborhood of omega 2. Question number 3. With the Quota method, I have to simulate the evolution of the rotation vector for an initial condition given here. and I have to draw the corresponding trajectory on the ellipsoid. So for the simulation, usually what we have to do, we have to take an initial condition, an initial state like this, and will correspond to omega r at time 0, like this. So it means that the body like this, you can have any shape, not always an ellipsoid. He have here the vector omega 1, omega 2, and omega 3 that are two coefficients, all these coefficients. Here omega 1, omega 2, omega 3. Take care, they are different. This one corresponds to a rotation vector. So what it means? It means when this body is rotating near this coefficient, like this, the body is rotating, this vector omega is a point in this ellipsoid. So this ellipsoid is not the body itself, it is a set of all rotation vectors such that the kinetic energy of my body, this one, is equal to 10. Okay. Now, for the simulation, what we have to do, we have to start with an initial condition and we have to follow the field. So for this, we may use an Euler method or Runge-Quota method. Here, we suggest to use a Runge-Quota method. So I will do something like this to follow, and probably I will come back here, and it is what I have to show by simulation. So for this, I will use a Runge-Quota method, and this Runge-Quota method is given by this iteration here. So it means that if at time t I am here, then I will have to follow the field. So the field corresponds to f, and it is given by the Euler formula. Let me recall that f of omega r is given by minus a minus 1 multiplied by omega r vector product I omega r. Like this. So this is my function f, and it is a Runge-Quota iteration. So I compute first this, and it will predict where I will be just a time further, and I will do an average between this vector and this vector, and will provide me a good integration. So I will be able to compute omega r at time t plus dt, where dt is small, from omega r. Now in practice, of course, there is, if the integration is good, if I start in the ellipsoid, just later I will be inside the ellipsoid. But it is not always the case if I integrate for a very long time. This is why in practice I will, it's better for long integration to take my vector which may go outside of the ellipsoid. It is sometimes important to project it, but I will not do it here. I will assume that this formula is sufficiently accurate for the time of integration I ask. Okay, so now I will start my program. The program I will consider is this Python program. Okay, so in this Python program, I initialize my vector here. It corresponds to omega r at time t equals 0. This is the t max, so I will integrate for 2.5 seconds, the time of integration, and it is my loop. So I will draw the row in blue so that I will be able to follow the trajectory like this. it will give me a path. And this is the Runge Quota integration. Okay. I switch to Python, given here. I start my program. I generate my file. I open it. And the trajectory is represented here. So I can see that I have started here. I follow the rows and I come back to my initial condition. I can see that I stay in the ellipsoid, and it is due to the fact that the vector field is always tangent to my ellipsoid. It is normal since the derivative of the kinetic energy is equal to 0, so the kinetic energy remains constant, and this one is an ellipsoid for which the kinetic energy is equal to 10. So now, of course, I have this oscillation which corresponds to a precession, which means that the body will not exactly have turn around its axis, principal axis, but there is some kind of oscillation, and this is called the precession. To understand the precession, so recall that I take my body like this, and here it is one of the main axes. I'll call it, for instance, omega 1. And if I am here, we can see the vector field is equal to 0, and it means that I am static. But I am static in this representation, so it means that omega dot r is equal to 0 if I am here. But for the body, it means that it is rotating at a speed of omega r. So take care when I say static. We should say a steady rotation. It is a static rotation if we want. Okay, so now about the precession, we can see that the omega r, the true one, is rotating. So let's say this one, for instance, omega r, is like this and rotates around this one. And we can understand this better if we look at this image of a gyroscope. Here it's a gyroscope with a spinning wheel, and we can see here a precession. So if due to this precession, the axis of rotation, which was represented by this this sharp here, I can see that I have a precession, and if the axis is static just at the vertical, so it means that I have no precession anymore. Okay, now for the last question, I have to simulate the evolution for another initial vector, and again, this vector, I have to check, as for this one, that it is in the ellipsoid. See, if I take this one, and if I apply this formula, then I get 10. Okay. Okay, so I'm here. I will change different things. Here the vector is not this one anymore. It is 0.01, square root of 10, and here 0. And I will integrate for a longer time, say 14. Okay. I will integrate this. I run it. And we can see that here I am just near to the second axis, principal axis, which is unstable as we have illustrated before. I come back here. Up. I take this file. It takes time. I see here the trajectory. So I start from here. Up. the trajectory, I start from here. The Runge-Quota method is quite accurate and follow here. And I switch from one principal axis, the one which is called intermediate, which is unstable. I will come back later here. So just to see with like this. So I start with this rotation. Later I will spin on the same axis and I will stay here for a few seconds, but the axes are changed. And after I will come back here periodically. So the period of rotation is impossible to predict because it depends on how far I am from the principal axis at the beginning. Okay, so this is known as the Zanibekov effect, which is known to be unstable. And in more general dynamical system, it is known as an heteroclinic path, because here I have some kind of saddle vector field where some components are stable. So this one is stable, and this direction is unstable. So I quit this equilibrium point on the unstable manifold, and I will come back on a stable manifold. So it is known to be an heteroclinic path.